Hello, my name is Marwan Baitzel, and today I will be giving a presentation on the basics of impact. So in impact loading, there are three main types. The first being a rapidly moving constant magnitude load, which is demonstrated by figure A. The second is a suddenly applied load, which is demonstrated by figure B. And the third is a direct impact load, which is demonstrated by figure C. And the difference between them is that in figure A, the gravity acting on the mass m is damped by the C, which is a plunger arrangement. In B, the mass is simply released onto the spring. And in C, the mass is able to gather kinetic energy before impacting the spring. Static versus dynamic loading. Whether a load is static or dynamic is decided by the time period in which the load is applied. The time period is given by the equation T equals 2 pi root m over k, where m is the mass and k is the spring constant. The practical difference between statically loaded and dynamically loaded objects is that statically loaded objects are designed to carry loads, while dynamically loaded or impacted objects are designed to absorb energy. And this can be seen in the case of a bridge versus a car crash. A bridge is statically loaded, as in the load is uniform and simply moving across the bridge, so the bridge must be designed to support that load. Whereas a car in a car crash must be designed so that it absorbs the energy of the car crash rather than transmitting it through to the passengers. And so in the case of static loading, the time period, in order for it to be static, must be greater than 3 times the natural frequency of the object. And for it to be dynamically loaded, the time period must be less than 1/2 of the natural frequency of the object. And there's a gray area in between those two values in which the load is neither static nor dynamic, just in the gray area. Deflection due to impact. In this situation, a mass falling onto a spring from height h, resulting in a deflection of delta with the equation delta equals delta static, which is the deflection after the mass has come to rest on the spring, times parentheses 1 plus root 1 plus 2h over delta static. From this, we can calculate the equivalent static force, which is the static force that would result in the same amount of deflection, using the formula Fe, which is the equivalent static force, is equal to the weight times parentheses 1 plus root 1 plus 2h over delta t. So essentially, all that's being changed is the delta static outside of the parentheses is being changed to the weight, which gives us the equivalent force. The deflection can also be calculated using the velocity of the mass at the point of impact by simply replacing the 2h within the parentheses and the root with a v squared and dividing by gravity, which gives us the equation delta equals delta static times parentheses 1 plus root 1 plus v squared over the force of gravity times delta static, which gives us the equivalent static force equation of Fe, which is the equivalent static force, is equal to the weight times parentheses 1 plus root 1 plus v squared over the gravity times the delta static. So essentially, we're just replacing the 2h with v squared and dividing by g, and the formulas remain the same. In cases where the deflection is much less than the height h, the following formulas can be used to calculate the deflection and equivalent static force. In that situation, the delta is equal to root 2h delta static, and the equivalent force is equal to root 2 WHK. And the delta is equal to root delta static times v squared over g in the case of velocity rather than height. And the equivalent force is equal to root v squared times kw over g. So essentially the same, simply replacing h with v squared and dividing by g.